Please subscribe to support the channel. Why does everything in the universe seem to spin? From the turning of the Earth to the swirling of galaxies, rotation is everywhere. A universal rhythm that connects the smallest particles to the grandest cosmic structures. Nothing in the cosmos truly sits still. Even atoms possess intrinsic spin at the quantum level. This endless motion isn't random. It's a clue to how the universe began. When the cosmos was born, it wasn't perfectly uniform. It was full of tiny fluctuations, uneven pockets of energy that set matter into motion. Over billions of years, those subtle twists and turns evolved into the rotations we see today. Planets spinning, stars revolving, galaxies spiraling. In a sense, the universe has been dancing since its first moment of existence, and everything we see, including ourselves, is part of that eternal spin. Nothing in the cosmos truly sits still. At first glance, space might appear calm and serene, a black canvas sprinkled with motionless stars. But this stillness is an illusion. The universe is in constant motion, from the smallest quantum particles to the largest superclusters of galaxies, spanning billions of light years. Every part of existence, at every conceivable scale, participates in a grand, unending dance. If you could somehow freeze the universe for a moment and look closer, you'd find that even what seems still is alive with motion. The atoms in your body are vibrating and spinning. The electrons circling their nuclei are in continuous quantum motion. The planet beneath your feet spins on its axis while racing around the sun at nearly 30 kilometers per second. The sun itself orbits the center of the Milky Way at over 800,000 kilometers per hour. Even the Milky Way is moving, rotating majestically, its billions of stars swirling like a cosmic whirlpool, while the entire galaxy hurtles through space toward the Virgo cluster. This relentless motion defines everything. There is no cosmic pause button, no resting state. Even the so-called empty space between stars is not empty at all. It teems with fluctuating fields and quantum vibrations, constantly giving rise to fleeting particles that blink in and out of existence. In this restless universe, stillness is not only rare, it's practically impossible. The very laws of physics favor motion. They preserve momentum, conserve angular momentum, and ensure that once something starts spinning or moving, it continues to do so unless acted upon by another force. From the moment of creation, the universe has been in motion, expanding, swirling, twisting, and evolving, in eternal ballet governed by gravity and the deep symmetries of nature. But here's the mystery that captures both the imagination of scientists and the curiosity of dreamers. What started all this spinning? Why does motion seem built into the very foundation of reality? Why didn't the universe begin in perfect, motionless balance? These questions peer straight into the heart of cosmology, the study of the universe's origin and evolution. To understand them, we must look beyond planets and galaxies and instead gaze backward in time, to the instant everything began, because somewhere in that first moment, when time and space themselves were born, lies the answer to why everything moves, why everything spins. Before the first stars ignited, before the first atoms formed, before even the first light streamed through the cosmos, there was energy. Pure, chaotic, and unimaginably dense. The universe was young, hot, and turbulent. It wasn't a serene explosion, but an eruption of existence itself, expanding from a singular point into what would become everything. In those first fractions of a second, space expanded faster than light, carrying energy and matter in every direction. And amid that explosive birth, motion, including rotational motion, emerged naturally. Because the universe wasn't perfectly uniform, not every region expanded at exactly the same rate. Some areas were ever so slightly denser and others slightly emptier. These minuscule irregularities, differences in density, pressure, and temperature, created gravitational imbalances that began pulling matter unevenly, forming the seeds of motion and spin that would grow over time into galaxies, stars, and worlds. To grasp the immensity of this idea, imagine the universe as an enormous ocean stirred by countless invisible currents. Each current represents a gravitational tug, a swirl of mass and momentum. Even a slight tilt or imbalance can cause rotation to begin. And once a region starts spinning, the law of conservation of angular momentum ensures it keeps spinning unless some powerful event slows it down. Over billions of years, these countless little rotations combined and evolved into the majestic cosmic structures we see today. The Earth spins because the cloud of gas and dust that formed it was already rotating. The Sun spins because the giant molecular cloud that gave it birth was turning. The Milky Way spins because the vast clumps of dark matter and gas that merged to form it carried angular momentum from those earliest cosmic instabilities. In other words, the motion we observe today is the echo of motions that began when time itself began. This realization changes the way we see the cosmos. Every sunset, every orbit, every spiral galaxy becomes a reminder of an ancient truth. The universe never stopped moving since the first instant of its creation. Every rotation we observe today is a ripple from that first cosmic breath. And perhaps, even deeper than that, motion itself might be an inseparable part of what it means for the universe to exist at all. Maybe stillness isn't natural, because existence itself implies change, and change implies motion. It's easy to imagine that there could have been a universe without spin, one that began perfectly uniform and stayed that way forever, silent and motionless. But such a universe would have been sterile and lifeless. Without rotation, there would be no gravitational clumping, no star formation, no galaxies, no planets. Everything we know and cherish depends on that initial imbalance, that cosmic stirring that gave rise to rotation. In a profound sense, we owe our existence to the universe's inability to stay still. And that brings us back to the most fundamental question of all. Why was the universe born with motion? Was it simply an inevitability of quantum fluctuations at the beginning of time? Or does motion reflect something even more fundamental about reality itself? That energy, matter, and space are never static, but forever dynamic. To explore that, we need to go deeper into what spin actually means. We need to distinguish between rotation, orbits, and intrinsic spin. Because understanding these different forms of motion will illuminate how the same principle governs everything from planets and stars to atoms and fundamental particles.
And so, as we move forward, we'll take a closer look at the nature of spin and rotation, what they are, how they differ, and why they matter so much to the story of our universe's endless motion. Before we can truly understand why everything in the universe spins, we need to clarify what spinning actually means. The word spin is often used loosely to describe any kind of circular motion, but in physics, it carries very specific meanings. There are two main kinds of rotational motion that shape the universe: spin, which is rotation around an object's own internal axis, and orbit, which is motion around something else. These two are deeply connected, but not the same, and understanding their difference helps unlock the mechanics of how planets, stars, and even atoms behave. Let's start with something familiar: our own planet. The Earth spins once every 24 hours around an imaginary line that runs from the North Pole to the South Pole. This is rotation on its own axis, and it's what gives us day and night. You can imagine it like a spinning top. The object itself is turning, even if it's staying in the same place in space. That's spin. But at the same time, Earth is also orbiting the Sun, completing one full trip around it every 365 days. That's a different kind of motion. Instead of rotating around itself, Earth is traveling in a curved path around another body. So while the planet spins on its axis, it simultaneously orbits the Sun. The Moon does both too. It spins on its axis and orbits Earth. Now here's where it gets interesting. These two motions often interact. The moon, for example, takes the same amount of time to spin once as it does to orbit Earth once. This is why we always see the same side of the moon. It's what scientists call tidal locking, a process where gravitational forces between two bodies synchronize their spins and orbits over billions of years. The same gravitational dance happens across the universe. Planets tidally lock to stars, moons lock to planets, and even stars in close binary systems can lock to one another. So, in simple terms, spin is when an object rotates about its own center, like the Earth turning once a day. Orbit is when an object moves around something else, like the Earth circling the Sun once a year. But of course, the universe doesn't move in such neatly separated categories. Spin and orbit are part of the same grand story. Both are governed by a physical quantity known as angular momentum. Angular momentum is the measure of how much rotational motion an object has, and it's one of the most conserved quantities in nature. That means once an object starts rotating or orbiting, it will keep doing so unless something external changes it, much like how a spinning figure skater turns faster when pulling in their arms. Let's visualize this more broadly. Imagine a massive cloud of gas floating in space, the kind that eventually collapses to form a star. Even if the cloud starts with a barely noticeable amount of rotation, as gravity pulls it inward, the cloud begins to spin faster and faster. This is because the total angular momentum of the cloud stays constant while its radius shrinks, just like an ice skater pulling in their arms. That's spin. Meanwhile, as clumps of gas form within this spinning disk, they begin orbiting the newborn star. That's orbit. Together, spin and orbit weave the structure of entire solar systems. We see the same principles in our own neighborhood. Each planet spins around its axis and orbits the sun. Some spin quickly, like Jupiter, which rotates once every 10 hours. Others, like Venus, spin slowly and even in the opposite direction. But no matter how unique their characteristics, both kinds of motion, rotation and orbit, obey the same fundamental physical law, the conservation of angular momentum. It's this law that ensures that once motion starts, it endures. Interestingly, these concepts aren't limited to celestial bodies. Even in our everyday world, we encounter spin and orbit constantly. A basketball spinning on a player's finger, that's spin. The same ball flying through the air in a curved path, that's orbit. The difference lies in what the motion is centered on, itself or something else. And yet, whether you're looking at a child's toy, a rotating planet, or a galaxy turning in the night sky, the underlying physics remains strikingly similar. But there's another level, a much deeper one, where the idea of spin becomes even more fascinating. At the atomic and subatomic scales, particles like electrons and protons also have something called spin. It's not spinning in the traditional sense. These particles aren't tiny spheres whirling in space. Instead, spin at the quantum level is an intrinsic property, a built-in form of angular momentum that determines how particles behave and interact. Without quantum spin, atoms wouldn't hold together, chemistry wouldn't work, and matter itself would collapse into chaos. So, this means that spin is not just a feature of large, visible things like planets or stars, it's a fundamental aspect of the universe's structure present even in the tiniest building blocks of matter. From electrons orbiting atomic nuclei to galaxies orbiting their gravitational centers, from the spin of an atom's core to the spin of a black hole, the same underlying idea applies. The universe seems to favor rotation. It's a natural consequence of how energy and matter organize themselves. So, when we talk about spin in the cosmic sense, we're talking about both the tangible rotation of objects and the intrinsic quantum-level properties that define everything in existence. Both are expressions of motion. Both are governed by angular momentum, and both trace their origins back to the earliest moments of the universe. Understanding this difference and connection between spin and orbit sets the stage for everything that follows. Because to explain why the universe is spinning now, we must understand where that spin first came from. And for that, we have to travel back to the very beginning, to the dawn of time itself, to the moment when the universe was born in fire, chaos, and motion. Next, we'll step back billions of years to that moment, the beginning of everything, to see how the seeds of spin were sown in the very first seconds after the Big Bang. To truly understand why everything in the universe spins, from planets and stars to galaxies and even particles, we have to journey backward in time, beyond the birth of our solar system, beyond the first stars, beyond the formation of atoms themselves. We must travel to the ultimate origin point, the beginning of the universe, the Big Bang. It's there in the earliest fractions of a second after creation that the roots of all cosmic motion were planted. The story of spin doesn't start with the planets. It starts with the universe itself being born in a storm of unimaginable energy and expansion. The Big Bang wasn't an explosion in space. It was an expansion of space. There was no center from which matter burst outward. Instead, space itself stretched and carried everything within it, like dots on the surface of an inflating balloon. In those first moments, the universe was searingly hot, dense, and unimaginably small. Every atom, every galaxy, every ray of light that would ever exist was compressed into an incredibly compact, high-energy state. And yet, even in that apparent simplicity, the seeds of complexity were already there. Tiny fluctuations, minute differences in density, and subtle irregularities in the otherwise smooth sea of energy. Those small imperfections are key. If the early universe had been perfectly smooth and still, no structures could have formed. There would be no stars, no planets, no galaxies, just a cold, uniform fog of particles drifting forever. But it wasn't perfect. Quantum fluctuations, microscopic jitters in the very fabric of reality introduced slight asymmetries. Some regions had just a little more mass and energy than others. These tiny variations, only one part in 100,000, became the gravitational bumps that started to pull surrounding matter inward. Over time, those pulls grew stronger, creating the first motions, the first flows of material, the first hints of rotation. As the universe expanded and cooled, matter began to clump together. Gravity, the great cosmic sculptor, took over. Wherever there was a little more mass, gravity pulled even more matter toward it. But these collapsing regions didn't fall inward perfectly symmetrically. They twisted. A slight imbalance, a tiny nudge in one direction, was enough to set entire clouds of gas and dust spinning. This was the beginning of cosmic angular momentum, the very source of all the spins we see today. It's fascinating to realize that the same fundamental forces that governed the spin of a planet also governed the swirling of matter in those first cosmic moments. The conservation of angular momentum, one of the most fundamental laws of physics, ensures that once something begins to rotate, it doesn't stop unless something forces it to. So when regions of the early universe began to collapse and twisting, that spin couldn't just vanish. It had to go somewhere. It became embedded in the structure of everything that formed thereafter. Even before stars and galaxies came into being, the universe was already moving. The cosmic microwave background, the faint afterglow of the Big Bang that we can still detect today, shows subtle patterns, like fingerprints left behind by those first ripples of motion. These temperature variations reveal that the young universe was full of swirling flows of gas and plasma, churning and expanding in every direction. Each swirl represented the earliest stirrings of rotation, the first whispers of cosmic spin. As time went on, these spinning regions of gas became the birthplaces of galaxies. Their angular momentum grew as they accreted more matter, pulling in streams of gas and dark matter that twisted and wound around them. What began as tiny, random fluctuations in the first seconds after the Big Bang eventually shaped the majestic spiral galaxies we see today, with their sweeping arms rotating gracefully around dense, luminous cores. The same initial imbalance that caused one cloud of matter to rotate slightly faster than another would, billions of years later,
determined the spin direction of entire star systems. But why were there fluctuations at all? Why wasn't the universe born perfectly even and still? The answer lies in the quantum nature of reality itself. At the smallest scales, even nothingness isn't truly empty. It teems with random fluctuations of energy due to the uncertainty principle. These quantum fluctuations are what gave rise to the first variations in density during the inflationary period, a brief, almost unimaginably fast expansion that took place just after the Big Bang. Inflation magnified those microscopic irregularities into macroscopic differences, freezing them into the structure of space. As the universe cooled and expanded, those slight differences became the seeds of cosmic motion and spin. In other words, the universe's restless and rotating nature is not a coincidence. It's a direct consequence of the quantum foam from which it emerged. The same unpredictable quantum jitters that defined the behavior of subatomic particles also shaped the grand structure of the cosmos. From the very first instance, the universe was never perfectly balanced, and those imbalances naturally gave rise to motion. To put it simply, spin exists because the universe began unevenly. Perfection would have meant stillness, and stillness would have meant nothing. The imperfections of the early universe were its greatest gift. They gave rise to motion, structure, and eventually life. The chaos of the beginning was not a flaw, it was the source of everything. So when we look at a rotating galaxy, a spinning planet, or even an electron's intrinsic spin, what we are really seeing is a continuation of the Big Bang's legacy. The motion we observe today, every orbit, every rotation, every swirl of gas and dust, is an echo of that first great expansion. To understand cosmic spin, then, is to understand the history of motion itself. Every turn of the Earth, every rotation of a star, is a direct descendant of the movements that began when time began. The next step in this story is to look closer at the state of the early universe itself, a time of primordial chaos, when energy, matter, and gravity began their intricate dance, setting the stage for all future motion and structure. The early universe, that first incandescent moment after the Big Bang, was far from calm or orderly. Though it expanded rapidly and evenly in a broad sense, when you look closer, it wasn't perfectly smooth. It was a sea of primordial chaos, alive with uneven distributions of matter, temperature, and energy. This chaos wasn't the destructive kind we associate with confusion or disorder. It was creative chaos, the kind that seeds complexity. Without it, there would be no galaxies, no stars, no planets, no life. The imperfections of the young universe were not flaws in its design. They were the sparks that ignited everything that would come afterward.
In the universe's infancy, about 13.8 billion years ago, everything was compressed into an almost uniform plasma. A hot soup of photons, electrons, protons, and neutrinos swirling together at unimaginable temperatures and densities. Yet even in that blazing uniformity, quantum physics ensured that absolute smoothness was impossible. Tiny fluctuations, literally the result of uncertainty at the smallest scales, cause certain regions to be ever so slightly denser or hotter than others. These differences might have been as small as 1 part in 100,000, but those microscopic variations became the seeds of all cosmic structure. Imagine the universe at that time as a vast, glowing ocean. In most places, the waves of energy were about the same height, calm, even, and consistent. But scattered across that ocean were tiny ripples, gentle rises and falls in density and temperature. Those ripples were the gravitational imperfections that would one day grow into galaxies and stars. Where the waves were just a little higher, meaning the energy density was slightly greater, gravity began to tug on nearby matter, pulling it inward. Over millions of years, these subtle differences became gravitational wells, drawing more and more material into them. The universe's first structures were born from these slight imbalances. We can actually see this ancient chaos today. The cosmic microwave background, or CMB, the faint afterglow of the Big Bang, is a snapshot of the universe when it was only 380,000 years old. To the naked eye, the CMB looks uniform, a smooth blanket of microwave light that fills the entire sky. But when scientists examine it with sensitive instruments, they see tiny variations, minute differences in temperature, just a few millionths of a degree. These differences are direct evidence of that primordial chaos. Each faint patch of slightly warmer or cooler light corresponds to regions of higher or lower density in the early universe. Those very patterns, those soft ripples in the cosmic ocean, eventually grew into everything we see. Clusters of galaxies, cosmic filaments, even the spinning planets orbiting distant stars. It's hard to overstate how important those early irregularities were. Had the universe been perfectly uniform, gravity would have had no direction in which to pull matter. Everything would have expanded evenly forever and no structures would have formed. But because of those fluctuations, certain regions became gravitational attractors. As these regions grew more massive, their gravitational pull intensified, and the surrounding gas began to swirl inward, not perfectly straight, but in curved, spiraling paths. This was the birth of angular momentum on a cosmic scale. The universe's earliest irregularities didn't just create density, they created motion. As those spinning clouds of matter evolved, they began to fragment into smaller pieces, each inheriting a portion of the larger cloud's angular momentum. The result was a cascade of spinning structures, from giant galactic halos to swirling nebulae to the rotation of individual stars and planets. Every spin we see today traces its lineage back to those original, quantum-sized imperfections in the fabric of the cosmos. In essence, the universe's spin was born out of its own unevenness. These primordial fluctuations were sculpted further by cosmic inflation, the period of incredibly rapid expansion that took place within the first fraction of a second after the Big Bang. Inflation stretched the universe from subatomic to astronomical scales, amplifying tiny quantum variations to macroscopic differences. What began as minuscule energy jitters were blown up to cosmic proportions, frozen into the fabric of space-time itself. When inflation ended, these differences remained imprinted, like faint fingerprints left on the universe's skin. As the universe cooled and expanded, those fingerprints became the framework for all future motion. It's hard to overstate how important those early irregularities were. Had the universe been perfectly uniform, gravity would have had no direction in which to pull matter. Everything would have expanded evenly forever and no structures would have formed. But because of those fluctuations, certain regions became gravitational attractors. As these regions grew more massive, their gravitational pull intensified, and the surrounding gas began to swirl inward, not perfectly straight, but in curved, spiraling paths. This was the birth of angular momentum on a cosmic scale. The universe's earliest irregularities didn't just create density, they created motion. As those spinning clouds of matter evolved, they began to fragment into smaller pieces, each inheriting a portion of the larger cloud's angular momentum. The result was a cascade of spinning structures, from giant galactic halos to swirling nebulae to the rotation of individual stars and planets. Every spin we see today traces its lineage back to those original, quantum-sized imperfections in the fabric of the cosmos. In essence, the universe's spin was born out of its own unevenness. These primordial fluctuations were sculpted further by cosmic inflation, the period of incredibly rapid expansion that took place within the first fraction of a second after the Big Bang. Inflation stretched the universe from subatomic to astronomical scales, amplifying tiny quantum variations to macroscopic differences. What began as minuscule energy jitters were blown up to cosmic proportions, frozen into the fabric of space-time itself. When inflation ended, these differences remained imprinted, like faint fingerprints left on the universe's skin. As the universe cooled and expanded, those fingerprints became the framework for all future motion. It's both humbling and beautiful to think that the grandest cosmic structures, spiral galaxies tens of thousands of light years wide, and the smallest quantum spins of particles share a common origin: chaos. The universe, it seems, was never meant to be perfectly symmetrical. In fact, the laws of physics don't favor perfect balance. They favor fluctuation, variation, and dynamics. Even the principle of symmetry breaking, a cornerstone of modern physics, tells us that whenever energy condenses into matter, perfect uniformity gives way to diversity. And in diversity, motion emerges. So the young universe was not a static, silent expanse. It was a dynamic, boiling, restless medium with every point in space slightly different than the next. These tiny irregularities were amplified over billions of years by gravity, forming galaxies that rotate, stars that spin, and planets that twirl. The chaos of the beginning didn't fade away. It became structure, stability, and ultimately beauty. Every galaxy spinning in the night sky today is a living relic of that early cosmic turmoil. This idea that disorder births order is one of the most profound truths in cosmology. Out of randomness came rotation. Out of chaos came creation. The universe's imperfections were the blueprint for its complexity. Without those early asymmetries, the cosmos would be nothing but a quiet, formless haze. With them, it became alive with motion and meaning. And now that we've seen how this primordial chaos set matter into motion, the next step is to understand how those tiny irregularities actually turned into real spinning systems. What was the mechanism that transformed slight density differences into swirling, rotating clouds of matter? The answer lies in gravity's timeless partnership with one of the most elegant principles in physics, the conservation of angular momentum. But before that, we must first explore how even the smallest irregularities in matter and energy began to create motion itself. How imbalance on the most minute scale became the architect of the cosmic dance we see today. The beauty of the universe lies in its imperfections. Those tiny asymmetries that existed in the early cosmos, the faint ripples of unevenness in matter, temperature, and energy, were not mere trivialities. They were the blueprint for everything that would follow. Because of these slight irregularities, some regions of the young universe had a little more mass than others, and that simple fact changed everything. It's astonishing to think that differences so small, fluctuations of just 1 part in 100,000, became the gravitational seeds from which galaxies, stars, planets, and eventually life itself would emerge. Gravity, though subtle, is relentless. It acts everywhere, all the time, pulling matter toward matter, shaping the cosmos into its grand architecture. In the early universe, where matter was distributed almost uniformly, these slight density differences acted as tiny gravitational hills. Regions with just a touch more mass exerted a slightly stronger gravitational pull, drawing in surrounding gas and dark matter. Over time, these areas accumulated even more material, becoming denser and more influential. This process is called gravitational instability, and it's the reason small variations in the early universe didn't fade away, they grew.
Now, here's where motion enters the picture. Matter doesn't simply fall straight into gravity wells. It almost never moves in perfect alignment. Even the smallest imbalance or offset in the way matter is drawn toward a dense region can introduce a sideways component, a slight twist. As countless particles of gas, dust, and dark matter began to drift toward these denser patches, their motions weren't perfectly symmetrical. Some material came from one direction a bit faster than from another. Some streams of matter collided at angles. These minor differences in direction caused the infalling material to start swirling. You can visualize it like this. Imagine rain falling into a puddle. If the drops fall evenly and directly, the water stays relatively calm. But if there's even a hint of unevenness, wind from one side, or drops landing at a slant, ripples and whirlpools form. The same thing happened on a cosmic scale. As gravity pulled matter inward toward those slightly denser regions, the flow wasn't perfectly head-on. The result? Rotation. Swirling motions began to develop naturally, and as they did, angular momentum, the measure of rotational motion, started to build up. These first cosmic eddies were unimaginably vast. clouds of hydrogen and helium gas stretching for light years, slowly spinning as they collapsed. But even though their rotations began weakly, the law of conservation of angular momentum ensured that the spin couldn't disappear. As each cloud shrank under its own gravity, it began to spin faster, just like an ice skater who spins more rapidly when pulling in their arms. Over millions of years, these swirling clouds became the nurseries of stars and planetary systems. The faint twists that began as small irregularities in the early universe evolved into the powerful rotations of celestial bodies we see today. The process was universal. Everywhere gravity gathered matter, it also gathered motion. Some of these early spinning clouds became proto-galaxies, vast clusters of stars bound together by gravity and rotating as one immense system. Others became protostellar nebulae, collapsing under their own weight until nuclear fusion ignited at their centers, giving birth to stars like our Sun. In each case, the original cause of their spin was the same: the universe's primordial asymmetry, amplified by gravity and preserved through time by angular momentum. It's remarkable to consider how delicate this process was. Had the early universe been just a bit more uniform, gravity might not have had enough direction to create spin. But had it been too chaotic, the universe might have torn itself apart before stable structures could form. The balance between order and disorder, between symmetry and imperfection, was so fine-tuned that it allowed the cosmos to develop both structure and motion. The universe didn't begin spinning because of some external force. It began spinning because imbalance is the natural state of things. Motion, in a sense, is what happens when perfection breaks ever so slightly. We can still observe the results of these ancient asymmetries today. Astronomers studying the distribution of galaxies across the universe have found that their spins aren't random. There are subtle, large-scale patterns, a kind of cosmic choreography, suggesting that the direction of spin can be traced back to those original conditions. Galaxies that form from the same primordial filament of matter often rotate in similar directions, their motions linked by the invisible threads of gravity stretching back billions of years. And this doesn't stop at galaxies. On smaller scales, these same physical processes determine how stars and planetary systems form. When a molecular cloud collapses to create a star, the gas and dust within it begin to swirl. As the material falls inward, it flattens into a disk, a protoplanetary disk, spinning around the newborn star. From that disk, eventually planets coalesce, each inheriting the direction and angular momentum of the original cloud born from tiny irregularities billions of years ago. But even as these large-scale structures formed, the process never stopped. The same principle of imbalance creating motion applies across all scales of the universe. The swirling of interstellar clouds, the twisting of galaxies, and even the spin of black holes all trace their origins to this fundamental rule. Wherever there is unevenness, gravity turns it into motion. Think about that for a moment. Every turn of the Earth, every orbit of the Moon, every spin of a distant galaxy began as a whisper of asymmetry in the first moments after the Big Bang. The universe has been twisting ever since, not because it was forced to, but because that's what imbalance does in the presence of gravity. Motion was born out of imperfection, and through that motion, the universe found its structure, its beauty, and ultimately its ability to create complexity and life. This realization also changes how we think about chaos itself. The word often carries negative connotations: disorder, confusion, randomness. But in the cosmic sense, chaos is the birthplace of order. It is the subtle irregularity that prevents stagnation, the necessary ingredient that allows creation to unfold. The swirling motions that define the cosmos are proof that perfection is not the ideal state of nature. Dynamism is. Without those slight differences in mass and energy, the universe would be frozen, static, and lifeless. With them, it became alive with rotation and evolution. And so, from the tiniest quantum fluctuations, amplified across billions of years, came the grand ballet of motion that fills the cosmos. Every galaxy that spins, every planet that turns, every atom that hums with internal spin is part of this ancient inheritance. The universe, once a sea of small unevenness, transformed that imperfection into the rhythm of existence. Next, we'll explore the key law that preserves this motion, the principle that ensures once something starts spinning, it keeps spinning unless an external force interferes. This law is the guardian of cosmic rotation, the reason the universe never forgets its initial movements, the conservation of angular momentum. At the heart of the universe's pervasive spinning lies one of physics' most elegant and fundamental principles, the conservation of angular momentum. This principle explains why motion, once initiated, persists indefinitely, and it is the rule that transforms tiny early asymmetries into the cosmic rotations we observe today. Simply put, angular momentum measures how much rotational motion an object has, and it is conserved, meaning that in a closed system, it cannot be created or destroyed, only transferred or redistributed. Once something starts to spin, it will continue spinning unless an outside force intervenes. This is why a spinning top keeps turning until friction gradually slows it, or why a planet keeps rotating for billions of years once set in motion. Angular momentum depends on two key factors: the mass of the object and how that mass is distributed relative to its axis of rotation, combined with the speed of rotation. The more mass that is distributed farther from the axis, the more angular momentum it has for a given rotational speed. Conversely, if an object contracts while conserving angular momentum, it must spin faster. This is why figure skaters can accelerate their spin by pulling in their arms, and why collapsing clouds of gas in space begin to rotate faster as they shrink under gravity. In this way, angular momentum acts as the universe's cosmic memory. It preserves the initial motion imparted to matter, amplifying it as structures condense and evolve.
The principle is astonishingly universal. Consider a spinning galaxy. The gas, stars, and dark matter within it are all participating in a coordinated rotational dance. This rotation didn't emerge from nothing. It is the amplified result of the very tiny initial spins created by the early universe's asymmetries. As the proto-galactic clouds collapsed under gravity, their spin rates increased naturally, conserving the angular momentum already present. Without this law, galaxies could not maintain their spiral structure. The stars would simply fall into the center. But because angular momentum is conserved, the material spreads out, stabilizes, and continues to rotate. Spiral arms form as a natural consequence, like ripples frozen in a rotating disk of matter. The same principle governs the formation of stars and planetary systems. When a molecular cloud begins collapsing, it doesn't fall straight inward in perfect symmetry. Even the tiniest asymmetries cause the cloud to twist. As gravity compresses the cloud, the conservation of angular momentum ensures that the spin intensifies. The cloud flattens into a rotating disk, the protoplanetary disk, with a dense spinning core at the center that becomes a star. Planets form from the dust and gas in the disk, inheriting the direction and momentum of the spin. This explains why most planets in our solar system orbit the Sun in the same direction and why their spins roughly align with that of the Sun. The conservation of angular momentum preserves the memory of the cloud's original motion. Angular momentum also explains peculiar phenomena like why Jupiter spins so quickly. Jupiter is massive, and during its formation, the contracting gas cloud conserved angular momentum, resulting in a high rotation rate. Saturn, Uranus, and Neptune display their own unique spin characteristics, shaped by a combination of initial angular momentum and later interactions like collisions and gravitational tugs. Even when impacts or tidal forces alter rotation, the principle still governs the redistribution of angular momentum. It is never destroyed, only shifted. At a more extreme scale, angular momentum dictates the behavior of black holes. A collapsing star that forms a black hole carries with it the spin of the original star. Conservation ensures that this spin is retained. often leading to incredibly rapid rotations. Some black holes spin at near the speed of light, twisting the very fabric of space-time around them. This is not merely a curiosity, it is a direct consequence of the universe's original motion, preserved and intensified through gravity and collapse. Angular momentum is also present in the microscopic world. Electrons have intrinsic quantum spin, a fundamental form of angular momentum. While it does not correspond to physical spinning like a planet or star, it obeys the same conservation laws. The spin of electrons and other particles governs the behavior of atoms, the formation of molecules, and the stability of matter itself. In a sense, the conservation of angular momentum links the tiniest constituents of reality to the largest cosmic structures. This principle is the reason the universe never stops moving. Once rotation begins, whether in a dust cloud, a star, or a galaxy, the motion is preserved, propagated, and passed along. That initial swirl caused by slight asymmetries in the early universe never dissipates, it only evolves. Even today, we observe clouds of interstellar gas, galaxies, and planetary systems spinning, all as living evidence of angular momentum's enduring influence. In practical terms, the conservation of angular momentum ensures that cosmic motion is self-sustaining. Gravity may pull matter inward, collisions may redistribute energy, and magnetic fields may transfer momentum, but the total rotational content of a system remains intact. This principle underlies every swirl, spin, and orbit we see, from the smallest electron to the largest supercluster. Without it, the universe would not be dynamic. Everything would simply collapse or dissipate. By linking initial motion with the vast structures we observe today, the conservation of angular momentum acts as a bridge between the universe's chaotic beginnings and the orderly rotations of galaxies, stars, and planets. It is a universal law that transforms the tiny ripples in the early cosmos into the magnificent, persistent spins we witness across billions of years. From the primordial stirrings of the Big Bang to the graceful rotation of the Milky Way, angular momentum is the silent law that keeps the cosmos twirling. Next, we will explore collapsing clouds of gas, the direct stage where gravity and angular momentum interact to transform primordial motion into the spinning stars and planetary systems that populate the universe.
The story of cosmic spin becomes tangible when we examine collapsing clouds of gas and dust, the cradles of stars and planets. In the vast expanse of space, giant clouds, composed primarily of hydrogen and helium, called molecular clouds, drift silently, stretching for dozens or even hundreds of light years. These clouds are the raw material of the universe, the primordial substance from which everything luminous eventually emerges. To the naked eye, they appear as dark patches against the starry background, or faint nebulae glowing under the light of nearby stars. But within them, a complex dance of gravity, turbulence, and angular momentum is quietly setting the stage for the formation of entire solar systems. A molecular cloud is rarely uniform. Some regions are slightly denser, colder, or more turbulent than others, a direct result of the primordial irregularities we discussed earlier. Over time, gravity acts on these dense pockets, pulling surrounding gas inward. Once a region accumulates enough mass, it becomes gravitationally unstable, meaning that the inward pull of gravity overcomes any internal pressure trying to hold it up. At this moment, the cloud begins a gravitational collapse, a process that can last millions of years but fundamentally reshapes the structure and motion of the cloud. Here's where the magic of spin becomes apparent. No molecular cloud is perfectly still. Random motions within the gas, slight asymmetries, and tiny initial rotations combine to give the collapsing cloud a faint spin. As the cloud contracts under gravity, something remarkable happens. Its rotation rate increases. This is angular momentum in action. The same principle we see when an ice skater pulls in their arms to spin faster applies on a colossal cosmic scale. As the cloud's radius decreases, its rotational speed rises, conserving the angular momentum it began with. A once-weak spin becomes a dominant feature, influencing the future structure of the system. As the collapsing cloud spins faster, centrifugal forces push outward, preventing the matter from collapsing directly into a single point. This causes the cloud to flatten into a rotating disk around a dense central core.
The core will eventually ignite nuclear fusion, becoming a star, while the surrounding disk contains gas and dust that may coalesce into planets, moons, asteroids, and other bodies. The rotation of the disk ensures that these secondary structures inherit the same direction of motion as the original cloud, preserving the angular momentum throughout the system. This process also explains why stars and planets generally rotate in a predictable manner. The direction of spin of the star and its orbiting planets is largely aligned with the rotation of the initial molecular cloud. That's why in our solar system, most planets orbit the sun in roughly the same plane and in the same direction. It's the cosmic fingerprint of the cloud's initial rotation preserved over billions of years through the immutable principle of angular momentum. Interestingly, not all collapsing clouds behave identically. Turbulence within the gas, collisions with other clouds, and interactions with nearby stars can introduce irregularities, tilt, or even reverse spins in certain regions. These disturbances account for the diversity we observe in planetary rotations and axial tilts. Uranus, for instance, spins almost on its side, likely the result of a violent collision during its early formation. Venus rotates backwards relative to most planets, possibly due to gravitational interactions or impact events. Even with these exceptions, the underlying principle is the same. Once motion is imparted to a collapsing cloud, angular momentum preserves and amplifies it. On a larger scale, entire star clusters form from sections of molecular clouds. Each star inherits a portion of the angular momentum of the parent cloud. The distribution of spin and motion among these stars is not random, but reflects the dynamics of the original cloud. Over millions of years, these clusters can disperse, with stars carrying their inherited motions across the galaxy. In this way, the earliest spins influence the behavior of stars far from their birthplace, linking the initial conditions of a molecular cloud to the ongoing rotation of stars and planetary systems throughout the galaxy. The process is mirrored in the formation of planets within the disks surrounding a young star. Dust grains collide and stick together, forming larger and larger clumps. These clumps continue to orbit and spin within the disk, gradually forming planetesimals and eventually full-fledged planets. Each new body preserves a fraction of the angular momentum of the system, meaning that the spin of planets, the tilt of their axes, and the orientation of their orbits are all inherited from the original motion of the collapsing cloud. Even small asymmetries in the distribution of mass can affect the rotation speed and axis tilt, which is why no two planets spin exactly the same way. Gravity, pressure, turbulence, and angular momentum work together in an intricate dance to transform a diffuse chaotic cloud into a structured, rotating system. What begins as a nearly invisible, gently spinning patch of gas becomes a luminous star with orbiting planets, moons, and rings, all moving in harmony. The same principles apply at larger scales. The spin of the molecular cloud eventually seeds the rotation of the galaxy that hosts the star system. Every rotation, therefore, is a link in a chain, stretching from the microscopic turbulence of gas molecules in a primordial cloud to the majestic swirl of galaxies. In essence, collapsing clouds of gas are the laboratories of the universe, where primordial motion is transformed into the tangible spinning structures we observe today. They illustrate beautifully how initial motion, no matter how slight, becomes amplified through gravitational collapse, producing stars, planets, and planetary systems. Angular momentum acts as both the architect and the historian, preserving the initial conditions and imprinting them onto the resulting celestial bodies. Next, we will follow the story from these rotating clouds to the birth of entire solar systems, where disks of dust and gas evolve into structured planetary arrangements, preserving the ancient spins and motions inherited from the primordial universe. From the collapsing clouds of gas and dust, the story of cosmic spin progresses naturally to the birth of solar systems. Once a dense core forms in a molecular cloud and ignites nuclear fusion to become a young star, the surrounding material, gas, dust, and ice, doesn't simply fall straight into the star. Instead, it forms a rotating circumstellar disk, often called a protoplanetary disk, because of the conservation of angular momentum we discussed earlier. This disk is the crucible where planets are forged, and its rotation establishes the fundamental orientation and motion of the entire planetary system. A protoplanetary disk is initially thick, turbulent, and chaotic, with gas and dust moving at different speeds and in slightly different directions. But as the disk evolves, gravity, pressure, and collisions cause it to flatten into a thin, spinning plane around the young star. Think of it like spinning pizza dough.
As it swirls, centrifugal forces spread it outward while flattening it into a disk. The flattening is a natural outcome of the interplay between gravity pulling inward and rotation providing outward centrifugal support. As the disk becomes thinner and more uniform, patterns of motion become established, and this is where the seeds of planetary orbits are set. Within the disk, dust grains collide and stick together, forming progressively larger clumps. Over thousands to millions of years, these clumps grow into planetesimals, small bodies ranging from a few kilometers to hundreds of kilometers across. The planetesimals themselves begin to attract more material through gravity, eventually forming planets. Throughout this entire process, the motion of the disk determines the direction of spin and orbit of the planets. Because the material in the disk is all moving in the same general rotational direction, planets inherit this rotation, orbiting the sun in the same direction as the disk spins. This explains why, in our own solar system, most planets orbit the sun counterclockwise when viewed from above the sun's north pole, and why most planets also rotate in the same direction as they orbit.
Yet the story is more intricate than simple inheritance. Collisions and gravitational interactions during planet formation can modify the spin and tilt of individual planets. A giant collision early in a planet's history can knock its axis off balance, producing extreme tilts like the nearly horizontal rotation of Uranus. The distribution of mass in the disk, the migration of forming planets, and resonant interactions between neighboring planets all contribute to subtle variations in spin rate and orbital orientation. Still, despite these complexities, the overall pattern is dictated by the initial spin of the disk, which itself derives from the original angular momentum of the collapsing molecular cloud. Protoplanetary disks also exhibit fascinating structural patterns that reveal the process of planet formation. Gaps, rings, and spiral arms observed in these disks are often caused by emerging planets clearing paths in the gas and dust. The rotation of the disk ensures that all of these features maintain coherence over millions of years. Even as planets migrate inward or outward, the conserved angular momentum of the system governs their motion, preventing chaotic collapse and preserving the organized orbital architecture. This mechanism explains not only the alignment of planetary orbits, but also the generally consistent direction of planetary spins. The initial rotation of the disk establishes the cosmic choreography of the solar system, embedding the primordial spin of the molecular cloud into every planetary body that forms. Every planet, moon, and asteroid becomes a participant in this grand rotational inheritance, a living record of the motions that began in the cloud long before the star itself ignited. In some systems, the alignment is nearly perfect, with planets orbiting in a well-ordered plane and spinning in harmony with their host star. In others, violent events, collisions, gravitational nudges from nearby stars, or interactions within the disk introduce irregularities, creating retrograde rotations or tilted orbits. Venus, for instance, spins in the opposite direction to its orbit around the sun, likely as a result of early collisions or tidal interactions with the sun. Uranus's extreme axial tilt suggests a massive impact during its formation. These exceptions highlight that while the disk sets the general direction of spin and orbit, chaotic events during formation can modify the outcomes, adding diversity to planetary systems. The formation of planets within a rotating disk is a powerful demonstration of how the cosmic spin is preserved and amplified. From the original asymmetries in the primordial universe, to the collapsing molecular cloud, to the protoplanetary disk, angular momentum is handed down at every stage, guiding the motions of stars and planets alike. The structure, alignment, and rotations we observe today are all echoes of the early spin, traced back through billions of years to the chaotic, uneven universe that existed just after the Big Bang. Ultimately, the birth of solar systems reveals a profound principle. Spin is not random. It is inherited, conserved, and reinforced, shaping every aspect of a planetary system's architecture. The planets in orbit, the tilt of their axes, and even the rotation of their moons all tell a story that stretches back to the first moments of cosmic motion. Each solar system, in essence, is a spinning record of the universe's history,
preserving the primordial dynamics that began when matter first started swirling in the aftermath of the Big Bang. Next, we will delve deeper into planetary rotation itself, exploring how each planet acquires its unique spin, speed, and tilt, and how collisions, internal dynamics, and gravitational influences shape the complex rotational behavior of planets. Once planets have formed from the spinning protoplanetary disk, they do not all spin uniformly. Each planet acquires a unique rotation rate and axial tilt, shaped by a combination of inherited motion, collisions, internal composition, and gravitational influences. While the overall direction of spin is set by the disk's rotation, the individual characteristics of each planet are determined by a variety of dynamic processes during and after formation, creating the diversity of rotations we observe across the solar system. The first factor influencing a planet's spin is the initial angular momentum inherited from the protoplanetary disk. As clumps of dust and gas coalesce into planetesimals and eventually full-fledged planets, they retain the general motion of the surrounding disk. This inherited rotation establishes the baseline spin direction, and most planets end up rotating in the same direction as their orbit around the star. However, the rate at which a planet spins can vary dramatically depending on its size, density, and the distribution of mass within the planet. A massive planet composed largely of gas like Jupiter can spin much faster than a smaller rocky planet like Mercury because its internal structure allows it to store and redistribute angular momentum differently. Collisions during the chaotic early stages of planet formation also play a significant role in shaping planetary rotation. The young solar system was a violent place, with countless planetesimals and protoplanets crashing into one another. A single large impact can dramatically alter a planet's rotation speed or tilt its axis. For example, Uranus's unusual sideways rotation is likely a result of a colossal collision early in its history, while Venus's slow, retrograde spin may have been caused by repeated impacts or tidal interactions with the Sun. Even smaller collisions contribute to incremental changes in rotation, cumulatively producing the wide variety of spin rates and axial tilt we see today. Internal composition and structure further influence a planet's rotation. Gas giants have thick, fluid interiors that can redistribute angular momentum internally, leading to differential rotation, the equator rotating at a different rate than the poles. Rocky planets, in contrast, have more rigid structures which constrain internal redistribution of angular momentum, stabilizing rotation over long periods. Molten cores, oceans, or atmospheres can also create subtle torques that gradually alter spin rates. On Earth, for example, tidal interactions with the Moon slowly reduce the planet's rotation speed over time, lengthening our days by a tiny fraction each century.
Gravitational tugs from nearby planets or the host star further modify rotation. These tidal forces can synchronize rotations over time, as seen in the Moon, which is tidally locked to Earth, always showing the same face. Similarly, Mercury's rotation has settled into a 3-to-2 resonance with its orbit around the Sun, a product of both its initial spin and prolonged tidal interactions. Even distant planets can influence one another subtly through resonances and gravitational nudges, producing variations in rotation rates or causing slow oscillations in axial tilt over millions of years. Taken together, these factors, initial disk spin, collisions, internal structure, and gravitational interactions, produce the rich diversity of planetary rotations. Mercury rotates slowly. Venus rotates backward. Earth spins moderately with a slight axial tilt that produces seasons. And gas giants like Jupiter and Saturn rotate rapidly, completing a full spin in under 10 hours. Each planet's rotation is thus a record of both its birth conditions and the chaotic processes that shaped it over billions of years. Planetary rotation also has profound consequences for climate, atmosphere, and habitability. A planet's spin rate influences the length of its day, the development of weather systems, and the stability of its magnetic field, which in turn protects the surface from cosmic radiation. The axial tilt determines the severity of seasons and the distribution of sunlight across the planet. In this way, the unique rotational characteristics of each planet are not just mechanical curiosities. They are fundamental to the conditions that make each world what it is. Even beyond our solar system, astronomers observe exoplanets exhibiting a wide range of spins and tilts. Some are tidally locked, some rotate extremely rapidly, and others exhibit unusual axial tilts, all reflecting the same combination of inherited motion, collisions, and gravitational interactions that shape the planets in our own system. The diversity of planetary rotations is therefore a universal phenomenon, rooted in the physics of angular momentum and the chaotic processes of planet formation. In essence, while the spinning protoplanetary disk sets the initial direction, each planet's individual characteristics emerge from the unique combination of environmental factors and formative events. The resulting spins and tilts are a cosmic fingerprint, a record of billions of years of collisions, gravitational influences, and internal dynamics, layered on top of the primordial motion inherited from the molecular cloud. Planetary rotation, in all its variety, is a direct descendant of the universe's earliest angular momentum, preserved and reshaped through the interplay of physics, chance, and cosmic evolution. Next, we will explore irregular spins and axes, examining planets that rotate in unusual directions or at odd angles, and what these tell us about the violent and chaotic nature of planetary formation. While most planets in our solar system follow a predictable pattern of rotation, not all spins are smooth or orderly. Some worlds defy expectations, rotating backward, on their sides, or at dramatically unusual angles. These irregular spins and axes serve as cosmic evidence of the violent and chaotic processes that shaped the early solar system, highlighting how collisions, gravitational tugs, and random events can drastically alter the rotational characteristics of planets. Take Venus, for example. Unlike most planets, Venus rotates retrograde, meaning it spins in the opposite direction of its orbit around the Sun. While Earth, Mars, and most other planets rotate counterclockwise when viewed from above the Sun's north pole, Venus turns clockwise. Its rotation is also extraordinarily slow. A single Venusian day, one complete rotation on its axis, lasts about 243 Earth days, even longer than its year of 225 Earth days. The prevailing explanation is that Venus experienced massive collisions or gravitational interactions in its early history, which either reversed its original spin or gradually slowed it to near standstill before eventually flipping it over. Then there's Uranus, which rotates nearly on its side. Its axial tilt is about 98 degrees, so the planet essentially rolls along its orbit rather than spinning upright. Such an extreme tilt almost certainly resulted from a catastrophic collision with a planetary-sized body during the formative years of the solar system. This violent impact would have knocked Uranus onto its side, completely altering the orientation of its spin axis. The result is unusual seasonal patterns, extreme variations in sunlight at the poles, and a system of moons that orbit along the same tilted plane, echoing the original impact event. Even Mercury, though not retrograde or sideways, has an unusual rotational pattern. Its rotation period is locked in a 3-to-2 resonance with its orbit around the Sun, completing 3 rotations for every 2 orbits. This is a result of tidal interactions with the Sun, a subtle gravitational tug over millions of years that has slowed and synchronized its spin relative to its orbit. While less dramatic than a catastrophic collision, this illustrates how gravitational forces alone can twist and reshape planetary rotations over time. The irregular spins of these planets underscore an important principle. The rotation inherited from the protoplanetary disk is not immutable. While motion persists, it doesn't prevent orientation changes caused by external forces. Collisions, close encounters with other bodies, and long-term tidal effects can all drastically alter both the speed and the direction of a planet's spin.
The resulting diversity reflects the chaotic and dynamic environment of early planet formation. Even smaller bodies, like moons and asteroids, display wildly varied spins and rotations. Some moons are tidally locked to their planets, always showing the same face. Others, like Saturn's moon Hyperion, rotate chaotically, tumbling unpredictably in space. This variability is a direct consequence of collisions, gravitational interactions, and irregular shapes, revealing that rotational chaos is a natural outcome of the universe's early dynamics. Interestingly, irregular spins provide clues about the history of collisions and interactions in a planetary system. By studying axial tilts, rotation rates, and orbital resonances, astronomers can reconstruct the sequence of events that shaped a planet's past. A retrograde rotation, for instance, might indicate a massive impact, while a highly tilted axis might point to gravitational perturbations or nearby encounters with other planets. In this sense, spin becomes a cosmic forensic record, preserving the violent and chaotic story of planetary evolution.
These irregular rotations also remind us that the universe is far from orderly. While angular momentum preserves motion, it doesn't dictate perfection. Chaos, randomness, and chance are woven into the formation of planets, leaving a diverse tapestry of rotations and orientations. Each planet's spin tells a story of inherited motion, of violent impacts, of gravitational nudges, and of the unpredictable interplay of forces during the universe's earliest formative periods. On a broader scale, these irregular spins mirror the dynamics of entire galaxies. Just as planets can rotate backward or on tilted axes due to collisions and gravitational interactions, galaxies themselves can display warped or irregular rotations when they interact or merge. In both cases, the cosmic choreography begins with primordial spin, but is continuously reshaped by the chaotic forces of the universe. The lesson is clear. While the universe favors motion and rotation, the outcome is never perfectly uniform. Irregular spins and unusual axes are evidence of a violent, dynamic, and evolving cosmos, a universe in which the inheritance of primordial motion interacts with chance and chaos to produce a rich variety of rotational behaviors. These exceptions, from Venus's retrograde spin to Uranus's tilted axis, are not anomalies, but natural outcomes of the processes that shape all planetary systems. Next, we will zoom out to the larger scale of stars and galaxies, examining how the principle of spin and angular momentum applies to these enormous structures, and how the rotation of entire galaxies is a natural extension of the same cosmic rules that govern planetary motion. As we expand our perspective from individual planets to the vast scales of stars and galaxies, the same fundamental principles of motion and spin continue to apply. Entire galaxies rotate, and their majestic spiral arms trace the path of cosmic angular momentum conserved across billions of years. The rotation of galaxies is a direct consequence of the initial motions imparted to matter in the early universe, amplified and redistributed over cosmic time, rather than newly created phenomena. Just as planets inherited spin from the collapsing clouds of gas in which they formed, galaxies inherit rotation from the primordial angular momentum of the matter that coalesced to create them. Galaxies begin their lives as enormous clouds of gas, dust, and dark matter. These proto-galactic clouds are enormous, hundreds of thousands of light years across, and like molecular clouds that form stars, they contain slight asymmetries in density, temperature, and motion. No part of the cloud is perfectly still. Tiny differences in velocity and density, amplified by gravity, lead to regions of preferential motion. As the cloud collapses under its own gravity, these small initial rotations are conserved, causing the forming galaxy to spin. Angular momentum ensures that as the radius of the cloud decreases, the rotational speed increases, just as we observed in molecular clouds forming stars and planets. The distribution of angular momentum within the cloud also dictates the final shape of the galaxy. For example, spiral galaxies like the Milky Way form from clouds where the rotation is fairly coherent, producing a flat, disk-like structure with stars orbiting the galactic center in roughly circular paths. Elliptical galaxies, by contrast, form from more chaotic collapses, mergers, or interactions that scramble the angular momentum of their constituent stars, resulting in a more spheroidal shape, with stars moving along random orbits. Yet even in these apparently chaotic systems, the total angular momentum of the original matter is preserved. It is merely redistributed among the many stars and other components of the galaxy. Gravity plays a dual role in shaping galactic spin. First, it draws matter inward, increasing rotational speeds as the galaxy condenses. Second, it mediates interactions and mergers between galaxies, transferring angular momentum and often spinning up or tilting entire systems. Galactic collisions, while chaotic and violent, do not destroy angular momentum. They redistribute it. This is why spiral galaxies often retain coherent rotation even after dramatic encounters, while elliptical galaxies emerge as smoother, less organized systems, but still obey the law of conservation of angular momentum. The rotation of galaxies is not a slow or trivial phenomenon. In spiral galaxies, stars orbit the galactic center at hundreds of kilometers per second, completing a full circuit over tens to hundreds of millions of years. The central bulge rotates more slowly, while the outer disk may rotate faster or slower depending on mass distribution, including the invisible influence of dark matter. These intricate rotational patterns reflect billions of years of history, tracing the motion inherited from the earliest proto-galactic clouds all the way back to the angular momentum present in the primordial universe. Stars within galaxies also carry angular momentum. Stellar nurseries, like the Orion Nebula in the Milky Way, are dense pockets of gas within a spinning galactic disk. Stars that form from these clouds inherit the local rotational motion, just as planets inherit spin from their protoplanetary disks. Over time, the collective rotation of billions of stars reinforces the overall spin of the galaxy, demonstrating the fractal nature of angular momentum. Motion is inherited and propagated from the smallest clouds to the largest galactic structures. Moreover, the spin of galaxies is not entirely isolated. It reflects the broader cosmic environment. Observations show that galaxies tend to align their rotation with the filamentary structure of the cosmic web. The large-scale network of galaxies, filaments, and voids formed from the distribution of matter in the early universe. This alignment suggests that angular momentum is imprinted on matter from the very beginning and preserved across scales from the smallest molecular clouds to the largest galactic filaments. Even as galaxies collide, merge, or interact gravitationally, the underlying spin of the system remains a fundamental property, a relic of the universe's earliest moments. Supermassive black holes at the centers of galaxies further illustrate the conservation of angular momentum at massive scales. As gas and dust spiral into these black holes, they form accretion disks, spinning at incredible speeds. The orientation and rotation of these accretion disks often align with the galaxy spin, linking the motion of the largest gravitational anchor in the galaxy to the motion of the entire stellar population. Once again, what started as slight rotational irregularities billions of years ago in the proto-galactic cloud becomes magnified and preserved through time. In short, the rotation of stars and galaxies is a natural extension of the universe's initial spin. These tiny asymmetries present in the primordial universe, amplified by gravity and preserved by angular momentum, cascade across scales, from quantum fluctuations to collapsing gas clouds to planetary systems, and finally to galaxies and galactic clusters. Spin is therefore not a coincidence or anomaly. It is a fundamental feature of matter in motion. The patterns we observe today are the result of a long chain of conservation, redistribution, and amplification of angular momentum across cosmic time. Next, we will examine the cosmic web itself, exploring how the largest structures in the universe, filaments, voids, and galaxy clusters, twist and rotate relative to each other, further demonstrating that spin is a universal property embedded in the very fabric of cosmic structure. When we zoom out even further to the largest scales of the universe, we encounter a structure so vast and intricate, it challenges human comprehension: the cosmic web. Stretching across hundreds of millions of light years, the cosmic web is composed of enormous filaments of galaxies and dark matter, interspersed with vast empty voids. These filaments are the scaffolding of the universe, guiding the formation and motion of galaxies, clusters, and superclusters. Remarkably, even at these unimaginable scales, spin and rotation remain fundamental features, revealing that motion is a property woven into the very fabric of cosmic structure.
Observations and simulations have shown that galaxy clusters within these filaments often exhibit coherent spins relative to the surrounding structures. Filaments themselves appear to twist and rotate, with clusters and superclusters aligned in ways that suggest inherited angular momentum from the primordial universe. In essence, the original motions embedded in the early universe, small asymmetries amplified by gravity, have cascaded upward from individual particles to planets to stars to galaxies, and now to the entire network of galactic filaments. Even on the grandest scales, the universe has retained its cosmic choreography. The formation of the cosmic web begins in the aftermath of the Big Bang, when slight density fluctuations in the primordial universe caused regions of matter to collapse along preferred directions. Gravity pulled material toward these slightly denser areas, forming elongated structures that eventually became filaments connecting clusters of galaxies. As matter flowed along these filaments, it acquired spin and angular momentum due to asymmetries in the collapse, tidal forces from nearby mass concentrations, and interactions with neighboring filaments. This means that the twisting motions of filaments and the spins of galaxy clusters are direct consequences of the initial distribution of mass and motion in the early universe. Computer simulations of large-scale structure formation vividly illustrate this phenomenon. When scientists model the evolution of the universe from the cosmic microwave background to the present day, they see filaments naturally develop rotations along their axes. Galaxies within these filaments tend to align their spins with the filament's orientation, creating a coordinated pattern of rotation across scales of millions of light years. This alignment isn't perfect. Chaotic interactions and mergers introduce variations, but the general trend is clear. Angular momentum persists and propagates even at the largest cosmic scales. The twisting of filaments also influences galaxy formation. Gas and dark matter flow along these filaments into clusters, carrying angular momentum that shapes the rotation of forming galaxies. Spiral galaxies tend to form in filaments where coherent motion dominates, while elliptical galaxies often arise in regions where collisions and mergers disrupt the original spin. The cosmic web thus acts as both a conveyor of matter and a preserver of rotational memory, imprinting the initial conditions of the universe onto the largest structures observable today. Moreover, the interplay between dark matter and baryonic or normal matter is crucial in shaping the spin of the cosmic web. Dark matter, which constitutes the majority of matter in the universe, collapses under gravity into vast halos that provide the gravitational scaffolding for visible structures. The angular momentum of these dark matter halos guides the formation of filaments and the rotation of galaxies within them. Even though dark matter cannot be seen directly, its presence is felt through the motions it imposes. subtly orchestrating the rotation of cosmic structures over billions of years. Observational studies using galaxy surveys and redshift measurements have confirmed that these rotational patterns are not merely theoretical. Filaments of galaxies stretching across tens to hundreds of millions of light years display statistical correlations in spin direction. Clusters embedded within these filaments often rotate in ways consistent with the larger structure, revealing a hierarchy of motion from the smallest galaxies to the largest cosmic formations. Even voids, the empty spaces between filaments, are influenced by this dynamic, with surrounding matter flowing along preferred directions that reflect the angular momentum of the broader cosmic web. The cosmic web demonstrates that spin is not just a local phenomenon limited to stars, planets, or galaxies. It is a fundamental property of matter and energy in motion, embedded in the very large-scale structure of the universe. The twists and rotations observed across filaments and clusters show that motion is conserved, inherited, and amplified across scales spanning millions of light years. The universe, in this sense, is not merely expanding, it is twisting, swirling, and spinning, a grand cosmic ballet choreographed by the laws of physics and the primordial motions set in place at the beginning of time. This large-scale perspective reinforces a profound truth. Rotation is intrinsic to the cosmos. From the earliest quantum fluctuations to the collapse of molecular clouds, to the spin of planets, stars, galaxies, and now to the entire network of galactic filaments, angular momentum acts as a universal thread connecting all scales of structure. The twists in the cosmic web are the ultimate testament to the enduring legacy of the primordial asymmetries that set the universe in motion. Next, we will zoom inward to the microscopic scale, exploring spin in the quantum world where even subatomic particles exhibit intrinsic spin, a fundamental property that mirrors the rotational patterns we see on astronomical scales, but governed by the principles of quantum mechanics. As we shift our gaze from the grand cosmic web back to the microscopic world, an astonishing realization emerges. Spin is fundamental not only on astronomical scales, but also at the quantum level. Subatomic particles, electrons, protons, neutrons, and even more exotic particles possess an intrinsic property called spin. However, unlike the rotation of a planet or a galaxy, this spin is not a literal physical rotation. Instead, it is a quantum property that defines the particle's angular momentum and plays a crucial role in the structure and behavior of matter. In classical physics, angular momentum is straightforward. An object rotates around an axis, and the rotation's speed and mass distribution determine its momentum. But in quantum mechanics, particles are point-like entities with no internal structure in the classical sense, yet they still carry spin, a discrete, quantized form of angular momentum. Electrons, for instance, have a spin value of 1/2 in units of the reduced Planck constant, h, meaning they obey the laws of quantum spin that cannot be visualized as simple rotation, but still profoundly influence physical interactions. Protons and neutrons also possess spin, and their combination determines the spin of atomic nuclei, influencing magnetic properties and nuclear stability.
Spin at the quantum level governs many fundamental phenomena. The Pauli exclusion principle, for instance, arises directly from the spin of electrons. This principle states that no two electrons can occupy the same quantum state within an atom simultaneously. Without this quantum spin property, electrons would collapse into the lowest energy state, and atoms, and therefore matter as we know it, could not exist. Spin also underlies magnetism. The alignment of electron spins in materials like iron produces macroscopic magnetic fields. In essence, the behavior of subatomic spins manifests as tangible effects in the everyday world.
Unlike classical angular momentum, quantum spin is inherently discrete. Particles can only take certain spin values, integers or half-integers, and measurements of spin along any axis yield specific outcomes, such as up or down for electrons. Yet despite its abstract nature, spin obeys conservation laws just like macroscopic rotation. When particles interact, whether through collisions, electromagnetic forces, or decay processes, total spin is preserved, demonstrating a remarkable parallel between quantum mechanics and classical angular momentum. This continuity across scales is profound. The same principle that causes a collapsing gas cloud to spin faster as it shrinks also governs how fundamental particles interact and maintain rotational properties. Spin is also at the heart of quantum entanglement and particle interactions. In atomic and subatomic processes, spin determines the probabilities of interactions, the formation of bonds, and the symmetry properties of matter. Particles with different spins behave differently in collisions and reactions, and these rules dictate the formation of complex structures, from atoms to molecules. Even photons, the particles of light, carry spin called helicity, which affects polarization and the transfer of angular momentum in light-matter interactions. In this way, spin unites the smallest and largest scales of existence. The angular momentum we see in planets, stars, and galaxies is mirrored by the intrinsic spin of electrons, protons, and other particles. Both obey conservation laws and shape the structures around them, though in profoundly different contexts. One is visual and tangible, the other is abstract and governed by quantum principles. Yet both demonstrate that rotation and angular momentum are woven into the very laws of physics, making spin a universal property from the subatomic to the cosmic. Moreover, quantum spin reminds us that motion is not just a macroscopic phenomenon, but a fundamental aspect of reality itself. Even in the ostensibly empty vacuum of space, particles with spin define the behavior of fields, forces, and energy. The persistent motion of the universe, from galaxies spinning in the cosmic web to electrons spinning within atoms, reflects a universe in which rotation is intrinsic, unavoidable, and universal. Spin is not just an emergent property of matter, it is a basic characteristic of existence, embedded in the fabric of space, time, and energy. By studying quantum spin, scientists can understand how microscopic rotations influence macroscopic systems. For example, the spin of electrons governs chemical reactions, material properties, and even technologies like semiconductors and magnetic resonance imaging. In every sense, quantum spin is the unseen engine behind the structure and dynamics of matter, providing a microscopic mirror to the grand cosmic rotations observed in stars and galaxies. Next, we will explore how all these scales unify, from quantum particles to galaxies, showing that spin is a continuous thread running through the universe, and revealing that motion is not merely common, but fundamental to the very existence of matter and energy. When we step back to look at the universe as a whole, a striking pattern emerges. Spin is everywhere, connecting the smallest subatomic particles to the largest galaxies and cosmic filaments. Despite the vast difference in scale, from electrons to protons, planets to stars, galaxies to the cosmic web, the principles governing rotation and angular momentum remain consistent. This continuity reveals that spin is not a random byproduct of cosmic evolution, rather it is woven into the very fabric of physical laws, fundamental to the structure and dynamics of the universe. At the quantum level, particles possess intrinsic spin, which dictates the rules for chemical bonding, magnetism, and the organization of matter. This spin is discrete, quantized, and governed by the principles of quantum mechanics, yet it obeys conservation laws. When particles interact, their total spin remains constant. This is strikingly similar to what happens on cosmic scales. A collapsing molecule cloud preserves angular momentum, a newly forming star or planet inherits spin from its disk, and an entire galaxy rotates according to the momentum imparted by initial conditions. In both cases, rotation is conserved, redistributed, and preserved, linking scales separated by orders of magnitude. The unifying principle here is that motion and angular momentum are intrinsic properties of matter.
They emerge naturally whenever mass interacts under the influence of forces, whether gravity, electromagnetism, or nuclear interactions. In a collapsing gas cloud, even slight asymmetries produce rotational motion. In the galaxy, the combined motion of billions of stars follows the momentum imparted by initial conditions. In the quantum world, spin is fundamental to particle identity and interaction. Across all scales, rotation arises from asymmetry, propagates through conservation, and influences structure, demonstrating a profound unity in the laws of physics.
Consider the fractal nature of this pattern. Microscopic spins combine to create macroscopic effects. The spin of electrons contributes to the magnetic properties of planets and stars, which in turn influence the dynamics of planetary systems and stellar formation. Galaxies carry the accumulated angular momentum of billions of stars, which themselves inherited rotational properties from their parent molecular clouds. Filaments in the cosmic web align their spins according to tidal interactions and initial asymmetries. At every level, rotation begets rotation, linking the tiniest to the largest in an intricate cosmic dance. Moreover, this unification highlights a profound principle. Spin is not merely motion in space. It is a fundamental descriptor of physical reality. On the largest scales, it determines the shape and behavior of galaxies and filaments. On the smallest scales, it governs quantum states, chemical bonds, and even the forces between particles. Motion and rotation are not optional features of the universe. They are intrinsic properties embedded in the laws of physics themselves. The persistence of spin across all scales suggests that the universe is structured around motion, with angular momentum as a guiding principle from the Big Bang to the present day. Even the processes that seem chaotic, planetary collisions, galaxy mergers, or turbulent molecular clouds, do not destroy spin, they redistribute it. This reinforces the idea that spin is fundamental, conserved, and persistent. It shapes the evolution of structures, the dynamics of systems, and the emergence of complexity throughout the cosmos. The fact that we see rotation from the scale of an electron to the rotation of a supercluster underscores that this is not coincidental, but a deep-seated property of reality. By unifying scales, we also gain perspective on the universality of physical laws. The same principle of angular momentum governs quantum spin, planetary rotation, stellar formation, galactic dynamics, and the twisting filaments of the cosmic web. It explains the consistency of physical processes, the predictability of motion, and the structural patterns we observe in the universe. Rotation is, in essence, a universal language linking the infinitely small to the infinitely large. This perspective allows us to appreciate that motion itself is a cosmic constant. The spinning of electrons ensures matter organizes into stable structures. The rotation of stars organizes energy and light. Planetary spins create cycles, climates, and seasons. Galactic spins shape spiral arms and stellar orbits. And cosmic web filaments maintain the largest scale flows of matter. Across these scales, spin is the connective tissue of the universe, revealing that movement is not incidental, it is intrinsic. Next, we will explore why the universe never stops moving, reflecting on how perpetual motion and rotation arise naturally from the birth of the cosmos, and why everything, from the smallest particle to the largest galactic filament, seems destined to keep spinning indefinitely. The universe is in constant motion, from the spinning of subatomic particles to the rotation of galaxies to the twisting of cosmic filaments. Motion appears to be a fundamental property of existence. But why is this perpetual movement so universal? The answer lies in the very birth of the cosmos. When the universe emerged from the Big Bang nearly 13.8 billion years ago, it did so not as a perfectly uniform still void, but as a seething, chaotic expanse filled with energy, matter, and tiny irregularities. These initial fluctuations in density, velocity, and energy seeded the motion that has persisted ever since. Nothing in the universe was ever truly at rest. The Big Bang imparted not just energy, but momentum, including angular momentum. This means that matter was born with tiny rotations and velocities, which were immediately acted upon by gravity, pressure, and other forces. Over time, these tiny initial motions were amplified and organized into larger structures. Molecular clouds began to collapse, spinning faster as they shrank. Stars and planets inherited rotation from their birth clouds. galaxies formed with coherent spins from their proto-galactic matter, and filaments in the cosmic web aligned and twisted as matter flowed along the gravitational scaffolding of the universe. At every scale, the initial momentum was conserved, redistributed, and amplified, producing the pervasive spinning and motion we observe today. Angular momentum is the key reason why the universe never stops moving. This fundamental law dictates that once an object or system begins rotating, it will continue to do so unless acted upon by an external torque. In the cosmos, external forces are rarely sufficient to halt motion entirely. Collisions, mergers, and tidal forces redistribute momentum rather than eliminate it. A planet may slow or tilt, a star may wobble, and a galaxy may warp or twist during interactions, but the total angular momentum of the system persists. In this way, the universe acts like a grand, self-sustaining dynamical system, where motion is inevitable, continuous, and enduring. Even on the largest scales, the motion of matter is evident. Galaxies are receding from one another due to cosmic expansion. Yet, within clusters and filaments, stars and galaxies orbit their centers of mass, following paths dictated by gravity and preserved angular momentum. Filaments twist and bend, guiding the flow of gas, dust, and dark matter, showing that motion is embedded not only in matter, but in the large-scale architecture of the universe itself. Energy and momentum were never evenly distributed. These primordial irregularities ensure that matter continues to flow, rotate, and evolve dynamically. The microscopic world mirrors this principle. Electrons, protons, and other particles spin intrinsically, obeying quantum conservation laws. Even in the apparent stillness of a vacuum, virtual particles fluctuate and fields carry momentum. Motion is woven into the fabric of reality, not as a contingent feature, but as a fundamental aspect of existence. From quantum spin to planetary rotation to galactic dynamics, the universe is never truly at rest. Its motion is a legacy of the Big Bang, written into matter, energy, and the laws of physics themselves. The persistence of spin across all scales suggests that the universe is structured around motion, with angular momentum as a guiding principle from the Big Bang to the present day. Furthermore, the ongoing motion of the universe is self-reinforcing. Collapsing clouds spin faster as they contract. Angular momentum prevents stars from collapsing into singular points. Planetary systems inherit spin that perpetuates orbital stability, and galactic interactions redistribute momentum without destroying it. Even chaotic or violent processes like supernovae or galaxy collisions do not eliminate motion. They transform and spread it, ensuring that the universe remains in perpetual flux. In essence, the universe never stops moving because motion is an inherent outcome of its origin. The energy and matter were never static, and the irregular distribution of mass and velocity ensured that angular momentum would persist indefinitely. Every rotation we see, from the twirl of a planet to the swirl of a galaxy, is a continuation of this primordial motion. The cosmos is a grand symphony of turning, flowing, and rotating matter, a universe in which stillness is almost impossible because movement is written into the laws that govern reality. Next, we will explore counterexamples and exceptions, examining objects that appear not to spin, why these exceptions are rare, and what they reveal about the universality of motion in the cosmos. Even though motion and spin are nearly universal in the cosmos, there are objects that seem to defy this trend, appearing almost motionless or devoid of rotation. At first glance, these counterexamples might seem to challenge the idea that everything in the universe spins, but a closer look reveals that even these objects are still governed by the fundamental laws of physics. Their apparent stillness is often a matter of perspective, measurement limitations, or the influence of external forces that mask their motion rather than eliminate it entirely. Take, for example, some planets and moons that rotate extremely slowly. Venus, as previously mentioned, rotates retrograde and completes a single rotation in about 243 Earth days, making its spin appear negligible compared to faster spinning planets like Jupiter. Mercury's rotation is similarly unusual, locked in a 3-to-2 resonance with its orbit around the Sun. In these cases, spin is present, but tidal forces from a nearby massive object, the Sun in both examples, have dramatically slowed or altered it. These tidal interactions redistribute angular momentum over long timescales, often synchronizing rotational and orbital periods, but they do not violate the conservation of angular momentum. They merely transfer it within the system. Similarly, some moons and smaller celestial bodies can appear to be non-rotating due to tidal locking. The moon, for instance, always shows the same face to Earth, giving the impression that it doesn't spin. However, this is an illusion. The moon completes a full rotation on its axis in exactly the same time it takes to orbit Earth. It is spinning, but the motion is synchronized with its orbit, demonstrating that apparent stillness can conceal underlying rotational motion. Many moons in the solar system exhibit this phenomenon, particularly those orbiting close to massive planets, revealing that tidal forces can dominate local rotational behavior. Magnetic fields and other forces can also disguise rotation. In highly magnetized stars or compact objects like neutron stars, interactions between the magnetic field and surrounding plasma can create patterns that obscure the object's spin when observed from Earth. Similarly, interstellar gas clouds may rotate extremely slowly or along axes difficult to detect, giving the illusion of near-zero rotation. In reality, careful observation often reveals subtle shifts in spectral lines, Doppler effects, or orbital motions that confirm ongoing rotation, even if it is minimal. Even seemingly stationary galaxies can have hidden spins. Some elliptical galaxies, particularly massive, older ones, may appear spherical and lack the obvious spiral structure of a rotating disk. However, these galaxies are not devoid of angular momentum. Rather, the rotation of individual stars is highly randomized. The net rotation is small or obscured, but the total angular momentum is conserved and distributed among billions of stars in various orbits. In other words, rotation exists, but its expression is subtle, embedded in the complex dynamics of the system rather than immediately visible. On a microscopic level, even particles that appear stationary in certain frames of reference still possess intrinsic spin. Electrons, for example, may occupy quantum states where their net motion seems negligible, but their intrinsic angular momentum persists, influencing magnetic fields, chemical behavior, and quantum interactions. There are no truly motionless particles. What we perceive as rest is always relative, and spin remains a constant underlying property. These counterexamples highlight a crucial point. True stillness is exceedingly rare in the universe. Objects that seem not to spin often have slow rotations, synchronized motions, or hidden spins that require careful measurement to detect. Even in systems dominated by tidal locking or strong magnetic interactions, angular momentum is conserved and continues to shape the object's dynamics. The exceptions do not undermine the universality of spin. Instead, they emphasize the richness and complexity of how motion manifests across different environments and scales. In essence, apparent non-rotation is almost always an illusion or a consequence of external forces, not an absence of spin. Whether slowed by tidal interactions, masked by random orbital orientations, or obscured by magnetic or quantum effects, these objects still conform to the fundamental principle that motion and angular momentum are pervasive throughout the universe. The cosmos may contain regions or bodies where rotation is subtle, but the underlying laws ensure that motion never truly ceases. Next, we will delve into the deeper question. Is spin merely a leftover from the Big Bang, or is it something more fundamental? A property intrinsic to the universe itself, woven into the interaction of space, time, and matter. As we reflect on the pervasive presence of spin throughout the universe, a profound and tantalizing question arises. Is rotation merely a relic of the Big Bang, or is it something far deeper, a fundamental property woven into the very fabric of reality? Up to this point, we have traced spin from the tiniest subatomic particles to entire galaxies and even the vast filaments of the cosmic web. And in each case, angular momentum appears as a conserved, persistent feature. But why does this property exist at all? Is this simply a leftover imprint of the initial chaos of the early universe, or does it represent a more intrinsic aspect of space, time, and matter? From one perspective, it is tempting to attribute all spin to the primordial asymmetries of the Big Bang. Tiny irregularities in density and motion at the universe's birth gave rise to all the rotations we see today. Collapsing clouds spun faster as they contracted, stars and planets inherited this motion, galaxies acquired rotation from proto-galactic clouds, and cosmic filaments twisted in accordance with the gravitational scaffolding of the universe. In this view, spin is essentially historical. It exists because the universe began in motion, and the law of conservation of angular momentum preserved that motion across billions of years. Yet this explanation, while compelling, may not capture the full story. Spin manifests in ways that transcend mere inheritance. In the quantum world, particles possess intrinsic spin, a property that has no classical analog. Electrons, protons, and neutrons spin not because they are physically rotating in space, but because spin is a fundamental aspect of their identity. This intrinsic angular momentum is quantized, unavoidable, and central to the behavior of matter. Its existence suggests that rotation is not merely a historical artifact, but a basic feature of the laws of physics themselves. Spin is baked into the equations that govern quantum mechanics, electromagnetism, and particle interactions.
On larger scales, the persistence of spin in galaxies and clusters, despite chaotic collisions and violent mergers, also hints at a deeper principle. Angular momentum is redistributed but never destroyed, and motion seems to be a natural outcome whenever matter interacts under the influence of forces. Even the cosmic web, with its vast filaments and twisting flows, demonstrates that rotation is not random but patterned, guided by the underlying structure of space and the interplay of gravitational forces. Spin, in this sense, may be more than an inherited feature. It could be a fundamental organizing principle of the universe, dictating how matter and energy behave across scales. Furthermore, spin appears to be intimately tied to symmetries and the laws of physics. Noether's theorem, a cornerstone of modern physics, tells us that conserved quantities, like angular momentum, arise from fundamental symmetries in nature. The existence of spin is therefore not accidental. It reflects deep symmetries in space, time, and the interactions between particles and forces. From this perspective, spin is as much a law of nature as gravity or electromagnetism. It is intrinsic, inevitable, and universal. This raises fascinating philosophical implications. If spin is fundamental, then the universe is intrinsically dynamic, never at rest. Motion, rotation, and angular momentum are not merely consequences of past events, but essential characteristics of existence. Every particle, planet, star, and galaxy is engaged in a perpetual dance, a reflection of the universe's inherent propensity for rotation. Even stillness is relative. Every object carries momentum, energy, or spin observable in some frame or scale. Motion is built into reality itself. Yet there is still room for mystery. Why exactly do particles possess quantized spin? Why does angular momentum manifest in such ordered patterns across billions of years and light years? These questions straddle the boundary between physics and philosophy, inviting us to ponder whether spin is both a product of the universe's birth and a fundamental rule woven into the cosmos, shaping matter, energy, and space-time itself. In asking whether spin is merely leftover or fundamentally intrinsic, we confront a profound truth. Rotation is a universal signature, an organizing principle that links the microscopic and macroscopic, the quantum and cosmic. It is a reminder that the universe is not static, not inert, but a dynamic tapestry in which motion is essential, inescapable, and deeply meaningful. As we pause to reflect on all we've explored, the sheer elegance of the universe's patterns of motion becomes impossible to ignore. From the smallest quantum particles to the spinning planets, from whirling galaxies to the twisting filaments of the cosmic web, motion is ubiquitous, persistent, and beautifully ordered even amidst apparent chaos. This is more than just a scientific observation. It invites a philosophical perspective. Perhaps motion itself is a kind of universal language of existence, a fundamental expression of the cosmos, signaling that stillness is almost impossible in nature.
Consider the fact that every particle carries spin, even if imperceptible to our senses. Every planet rotates, every star spins, every galaxy turns. Even on the largest scales, matter flows along cosmic filaments, twisting and redistributing angular momentum across millions of light years. This pervasive rotation is not a random accident. It reflects underlying laws, symmetries, and principles that govern the universe. In this sense, motion is the voice of physical law, expressed across scales and time. To observe it is to witness a profound continuity, a rhythm that connects the infinitesimal to the infinite.
There is a kind of poetry in this realization. Imagine the electrons in your body spinning in quantized states, the Earth rotating beneath your feet, the sun's slow rotation, and the Milky Way swirling in space. These motions are all interconnected, not in a mechanical sense, but through the principles of angular momentum and conservation laws. The universe, in every corner and at every scale, is alive with movement, a ceaseless dance in which energy flows, matter turns, and patterns emerge. Stillness, if it exists at all, is fleeting and relative. It is the exception in a cosmos fundamentally defined by motion. Philosophically, this view challenges our human intuition. We often think of rest as normal and motion as something extraordinary. Yet when we observe the cosmos in its totality, the opposite appears to be true. Motion is normal, rest is rare. It is the natural state of existence. Every spin, orbit, rotation, and oscillation is a manifestation of the universe's intrinsic dynamism. In a way, the universe speaks to us through these movements, inviting awe and curiosity, reminding us that we are participants in a larger, ever-turning reality. This perspective also carries a sense of unity. The same laws that dictate the spin of an electron also shape planetary rotation, stellar dynamics, and galactic motion. The language of rotation and angular momentum is universal. It transcends scale, time, and location. By observing these patterns, we are reading the universe's story, a narrative written not in words, but in motion, revealing the deep interconnections between all forms of matter and energy. There is a subtle humility in this reflection. The universe moves and spins with a grandeur far beyond human comprehension, yet it does so according to principles that we can study, understand, and appreciate. The ceaseless activity of the cosmos suggests that to exist is to move, to interact, to change. Even when we experience moments of stillness in our daily lives, we are embedded in this cosmic ballet, carried along by forces, rotations, and flows that began billions of years ago and will continue long after. Finally, pondering the ubiquity of spin encourages us to see the universe as dynamic rather than static, as a symphony of movement rather than a frozen scene. Motion is not just a physical property, it is a metaphor for existence itself. The twirl of galaxies, the spin of planets, and the rotation of atoms all whisper the same truth. The cosmos is alive with energy, eternally flowing, and motion is its most fundamental expression. Stillness may exist in localized pockets, but it is temporary and relative. The universe, in all its scales and forms, is defined by movement, a grand ongoing dance of creation, preservation, and transformation. Next, we will bring all these ideas together in a closing thought, reflecting on why everything spins and illustrating the cosmic choreography that links atoms to galaxies and past to present. As we draw this exploration to a close, one central truth emerges. Everything in the universe spins. From the tiniest electrons to the largest galaxies, from the whirling clouds of interstellar gas to the twisting filaments of the cosmic web, motion is everywhere, conserved and persistent. The reason for this ubiquity of rotation is both simple and profound. The universe began in motion, with energy, matter, and angular momentum distributed unevenly in the aftermath of the Big Bang, and it has been conserving and redistributing that motion ever since. Planets inherited spin from collapsing protoplanetary clouds. Stars and galaxies inherited spin from the collapsing clouds of gas and dark matter in which they formed. And cosmic filaments carry angular momentum inherited from primordial density fluctuations.
Even at the quantum level, particles possess intrinsic spin, a fundamental property that governs their interactions and underpins the structure of matter itself. Across every scale, rotation is preserved, amplified, and expressed, a continuous thread linking the very small to the very large, the young universe to the present. The universe's motions are not random. They are the manifestation of deep physical principles, the conservation of angular momentum, the symmetries of space and time, and the natural response of matter to gravity and energy. Collisions, mergers, and chaotic interactions redistribute momentum rather than erase it, ensuring that motion is not lost but transformed. Even in objects that appear still, subtle rotations or tidal interactions confirm that absolute rest is exceedingly rare. The cosmos is dynamic by design. Viewed holistically, this spinning is a kind of cosmic choreography, a grand dance in which every object participates. Galaxies swirl gracefully through the void, stars rotate in orbit, planets spin and tilt, electrons twirl in quantum states, and even the filaments of the cosmic web twist and flow over unimaginable distances. Each rotation, each orbital motion, and each spin is a movement in an ongoing performance that began with the birth of the universe. Motion is not just an occasional feature of reality, it is the defining characteristic of existence itself. The beauty of this insight is not only scientific, but also philosophical. Motion connects all things, providing a unifying thread through the complexity of the cosmos. It reminds us that stillness is the exception, that energy and matter are fundamentally dynamic, and that the universe is alive with ongoing processes that span scales, time, and space. From the twirl of an electron to the swirl of the Milky Way, the cosmos is an eternal dance of energy and motion, a grand choreography of spin that speaks to the very nature of reality.
In the end, everything spins because motion is built into the universe, from its first moments to its current state, and will continue to be expressed in countless forms for billions of years to come. The dance of galaxies, the rotation of planets, and the intrinsic spin of particles are all part of the same magnificent pattern. A reminder that the cosmos is never still, never silent, and forever in motion. Spin, in every sense, is the heartbeat of the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.